I'm talking about this subject, but if I understand correctly, the audience is like a mixture of the physicist, chemist, biologist, mathematician. So I did some work for the chirality things, but I probably better to talk about the more general topics because that might be best for the many audiences. But anyway, the title is a bit formal, so it doesn't work. Why doesn't it work? あれしか動いてるのな、不思議だな。
どっかシェアされてない。シェア。
あれ謎だな。
But I think you must click on the presentation. Just click in the slides.
What?
Yeah, click. Yeah, click on that. Anywhere.
Click.
Yeah.
Okay.
Now I can see the number.
Oh, yeah. Thank you. It's mysterious. So I put a bit more informal title. The secret of open quantum dynamics theory that no one told you. The second one is the doctor equation I told you. And the truth of the quantum thermodynamics or something like that. And then let me start from this one. So the basic idea of the open quantum dynamics. And so, you know, many people are probably not so familiar with. So about the model. So I think this might be the best way to introduce how we construct the what's called system bus model. And so this open quantum dynamics theory is, you know, that consists of the main system and the heat buses. And it is quite useful in the chemistry because many chemical processes are occurred in the environment, like a condensed phase, like a biological system, something like that. Then the point is we have a system and heat buses. Then how we can model it. So this is for my paper about machine learning to construct a system bus model. And this was my student, Mr. Ueno, and so he is very good about, you know, this kind of the machine learning things. So that this is one example. So this is a molecular dynamics simulation of the MD. So we want to construct a model for this water about for optical spectroscopy. So these are the intramolecular mode of the waters. Then they are each other, you know, interact with. So this part, like each mode, like a 3 mode, and harmonic mode, then interaction like here. Then another mode, what's called the intermolecular mode, you know, we consider using the heat buses. Then point is, so that this heat bus, you know, this system interact with this heat bus for some specific frequency. The P of this model is what called spectral distribution function, J of omega. So using machine learning, what we did was, so we ran the MD simulation, then chose the anharmonic parameter, coupling parameter, and this spectral distribution, so that each mode has a different spectral distribution. For example, this stretching mode is coupled to the low frequency, like a vibrational mode like that. Then the algorithm, so by the way, so the Mr. Ueno is good at for writing the cartoon. So this is a you know, JCTC. So he drew this picture like here. But anyway, so the MD simulation, so we took the coordinate, then try to, you know, optimize the coordinate using this model. So choose the J of omega like that. So this is one example. Another one is like a biological system, like there are a lot of quantum, you know, process all kind of biological system, like a Hall transfer, electron transfer, like extron transfer. So these cases like DNA, electron pole transfer, and this is a chromophore and electron transfer, and this is a extron transfer. Then this kind of the system is studied by what's called two-dimensional spectroscopy. So, to simulate this two-dimensional spectroscopy, almost impossible to do that by MD or QMM or something like that. So we have to use a system bus model. So this is another paper. So this is another cartoon. So we use this model. And so this extron system, extron transfer, these are two-level system, and there are interaction between them. So this is each molecule has like excitation, homoloom things. Then the heat bursts. Heat bursts is like here and here. So what we did was systematic integral heat burst, J of omega, and J of omega is something here. Then draw the simulator to this spectrum here. And this is all flow. So the like a QMM kind of a simulation. So we take the trajectory of the homolumo. Then so this is the trajectory of a homolumo. Then using this model, system bus model, we try to map this one. Then obtain the spectral distribution. Then calculate like this one. So this is like a things. Then I now talk about open quantum diamond theory. So this system consists of the main system and the heat burst. And so in this case, main system is like a 3-level system or 2-level system of the heat bursts. So the heat bursts do very special things. So it supplies the energy to the system. It's called fluctuation, or take out the energy from the system. It's dissipation. And the equilibrium state is, obtained when the energy supplied by the fluctuation and the energy get rid of the dissipation are balanced. And that is the thermal equilibrium states. But the many theory actually doesn't describe the right thermal equilibrium states. There is a fact called Lindenblatt equation or quantum master equation. These equations cannot describe the thermal equilibrium states correctly because they don't have either fluctuation or dissipation here. But then, so another important issue for this system. So total thermal equilibrium state is like here. So beta is the inverse temperature. But many cases, this thermal equilibrium state is assumed. It's what's called the factorized equilibrium state. So ignore the interaction part. So many people assume that what's called detailed balance to have this open quantum dynamics theory, but actually detailed balance, assuming this thermal equilibrium state. So that also doesn't work. So the many formalism actually does not describe the correct. Then so the total system. So now the heat burst is we usually employ the ensemble of the harmonic oscillators, and then as I say, this heat burst is characterized by the spectral distribution. So it's like a sum of the heat burst. Then there is a very tricky part here. So here, it is like a discretized function, but we introduce continuous function. So by doing so, we are effectively introducing the infinite number of the heat bursts. So that means the heat capacity becomes the infinity. Then we have a time irreversibility, and the total system goes to the thermal equilibrium states. Then so to describe this kind of the problem, we usually use a fact called the reduced density matrix. So this is a wave function. For the Q is a system, X is a heat burst coordinate, ensemble of the heat burst coordinate. So this is a regular wave function, but we must think about the density matrix. So this is the left-hand side wave function, this is the right-hand wave function. And this follow the equation of motion for this is what's called the Liouville equation, quantum Liouville equation. But it's the same as the Schrödinger equation. But then, so this one is it's a linear equation, and so the time reversal. If you change the t to minus t, so the dynamics goes back. But then we will going to have a time universal dynamics as I explained like this way. So anyway, so this is a density matrix. Then suppose we are measuring like dipolar molecule of the polar molecule in like a non-polar solution like this one. So we shine the laser, then laser does not interact with the non-polar solution, just with the system. And the system has a dipole, it's a function of the Q system. So this is the expectation value of this dipole. So the expectation value that both trace A and plus B. Then point is that we have a trace A and B. However, trace B is not a function of Q is a dipole is not a function of the coordinate, the bus, so go like here. Then we replace this part like here. So this is called the reduced density matrix. Once we reduce the heat plus degree of the freedom, the equation of motion is no longer time reverse. We have some extra terms like here. And so it is like a complex usually. Then irreversibility appear. The reason we have irreversibility is following. So actually, not just the time irreversibility. So the energy conservation law is also broken. But the original one is, it's all the energy is, hold. But the reason we don't have energy conservation law is because this one, we're just looking at here, not the entire system. This is for the entire system, but this is just for here. So the energy of this one does not necessarily to conserve. So if this is excited, this energy go to the environment. But if environment is hot, the energy go to the system. So that's why this reduced density matrix has a time irreversibility. And the important thing is that this environment has an infinite degree of the freedom. So the heat capacity is infinite. That's why if energy given to the environment, temperature doesn't change. Then now I explain the formalism I'm going to use, what's called the hierarchical equation of motion. Then for this purpose, I briefly explain the path integral formalism, very, very briefly. So this is the Schrödinger equation. And the formal solution of the Schrödinger equation is here. So this is what called green function. This is a formal solution. Then path integral, so this green function is like this form. It's like what called a functional integral. And the S is actually the action, is actually the time integral of the Lagrangian. But actually, the definition of this path integral is, so this is a Lagrangian, something like so. So this is actually the multi-dimensional integral for in the coordinate space and for like this evolution. So anyway, so this is you may think that a Schrödinger equation is written in a bit different way. And if you're interested in my homepage, I have like a lecture note like here for the PowerPoint lecture note. But anyway, so then I just formally use this expression. It's more convenient because Q is now the C number. Then now we have a system and heat bus. So the total the wave function. So the heat bus part, the system part. So this is the action of the system part, the heat bus part, action of the heat bus part, and the system bus interaction. By the way, I dropped the H bar because a bit complicated, I'm a bit lazy. So this is the wave function. Then what we're looking at is this reduced density function. So the initial equilibrium states and left-hand side wave function like here, and the right-hand side wave function. So this is the initial states. Then trace B. So this is a reduced density matrix. And so the important point is that this thermal equilibrium states is like written like this one. And as I say, it's not factorized form. It's called the entangled, non-factorized. The system and the heat bus is entangled, like here. And so I will introduce what's called influence functional formalism. And what I found was that if I started from this initial condition, it's much, much easier to derive the influence function. That's why it's better to use this one. anyway, then, this is a thermal equilibrium state. Thermal equilibrium state is like here. It's similar to the wave function, but now it's real time. So it's what called weak rotation, so that we can change IT to beta, then we have this one. So this is a thermal equilibrium state. And this is actually just right for in the path integral form for this. But for when the heat burst is harmonic, so we can carry out a path integral. So it's like a Gaussian integral. So actually we can perform the path integral representation here. So this is a partition function for the thermal equilibrium states, like here. And this is just a heat burst part. So this is like a Gaussian integral. So actually, after we conduct a Gaussian integral and trace over B, then we have this one. So this is a expression for the thermal equilibrium states. So this is this part. Then using this one, we can derive the inference function. So this is again, I just wrote the reduced density matrix. And in path integral form, it looks a bit complicated, like a left-hand side wave function, right-hand side wave function, like the equilibrium states are right-hand side wave function. I just changed the order of the time for, so for convenience. But what I found was, that they are actually the similar form. So if I define what called the complex, the counterpart like here, and this expression reduced to this one, like here. So that we must evaluate this one along this one, but anyway, this one. And this form is, I just showed in the previous slide. So this is the result. So once we go to this result, then put this counterpart into the here. So we have an inference function here. And detail is not necessary, but the important thing is it has a particular fluctuation and dissipation. And some other term, I don't talk about this part, but anyway, it has a fluctuation and dissipation. I will discuss this in a bit later, but anyway. Then, so I will show that I can obtain what I call the hierarchical equation motion from the time derivative of this reduced density matrix here. And this expression is non-perturbative form. So because I did not do any approximation to obtain the inference functional, so it's contained all order of the system bus interaction. So this one, if we expand this F in terms of the system bus interaction, it's Gaussian integral, so we already have an even number. The first order is a 2, the second order 4, like here, then 6 like here. Then so that it's like came from the commutator like here. And important fact is that this diagram contains like this part. So the left-hand side, this represents the left-hand wave function. This is the right-hand wave function. This is the phonon emission absorption and phonon emission absorption. And some diagram, so left-hand side wave function emit the phonon, then right-hand side wave function absorb the phonon. So this is not L-meet, The left-hand side wave function and the right-hand side wave function is like a communicating each other. That's why the time irreversibility appears. So this is a non-Hermitian diagram. So this is the key point of the heat burst kind. So, and the conventional theory, relative field theory, quantum mass theory, like Lindblad, is all the second one. But the theory I'm going to explain the non-perturbative. Then the second theorem, now the hierarchical equation motion. So as I say, we have 4 terms, and the first 2 terms are very important. Then it's called one is the dissipation and the fluctuation. And that describes the phonon emission absorption like this one. And there is also cross term like here. So the fluctuation, beta is the inverse temperature. So the temperature dependent. Dissipation is a temperature independent. So the fluctuation, if you are familiar with the Langevin equation, it's like a Langevin random force. So correlation function of the Langevin random force corresponds to the fluctuation. Then dissipation is a damping in the Langevin, kernel. And this dissipation and fluctuation relates to the so-called fluctuation dissipation theory. And if fluctuation dissipation theory are not satisfied between these two, you cannot get the right thermal equilibrium states. So that's what you need to know. Then there are some other terms. It's like actually, explaining about the entanglement between the heat of Earth and some system dynamics, but I can skip this part. Then, so that I plotted this dissipation and fluctuation for some specific spectral distribution. And this is a dissipation. So this case is like an exponential decay function. So it's called what's called a non-Markovian. So that if this is a delta function, it's called Markovian. Actually, if gamma is very large, it's go to the delta function, so it's become Markovian. So this, involves the Markovian limit. But for the dissipation. But fluctuation, so fluctuation, there are some additional terms here. And this part is called Matsubara frequency. And because of this Matsubara frequency, the correlation function of the fluctuations exhibit a very strange behavior. So this is actually the zero. So, and if temperature is very low, this fluctuation, the correlation function of the fluctuation becomes negative. So for Langevin, it's never appear because the Langevin is classical equation motion. But we are dealing with a quantum noise. So the quantum noise, actually, for low temperature, it has a negative part. And also, this part is independent from gamma. So this is from the quantum noise, and it's always non-Markovian. So many people assume the Markovian assumption for both dissipation and fluctuation, but this is actually unphysical. So if you assume the unphysical condition, then you will have what's called the positivity problem. Some catastrophic behavior appear. And that happens because this Markovian assumption is unphysical. But anyway, so this case, I derived hierarchical equation motion for simple case for demonstration purpose. And when both fluctuation and dissipation, so high temperature case for fluctuation and dissipation is like this form. Then this is a left side wave function action, right hand side wave, and this is a wave influence function. And so this is just I rewrite the previous result. And obtaining hierarchical equation motion is very simple. I just consider the time derivative of this one. So this is the exponential function here. As I say, this contains all order of the system-bus interaction here. And this part, blue part, is like a phonon emission. And the red part is a phonon absorption. And there is a time delay that describes the non-Markovian noise. And this part is the temperature independent, it's a dissipation, and this is a fluctuation. And fluctuation dissipation theory is satisfied, as I said. Then time derivative of consider the time derivative of this rho zero. Then the time derivative of the rho zero consists of the time derivative of this part, this part, this part. And this part, time derivative of this part is actually the Hamiltonian is here. It's like from this theory in the classical mechanics, but the quantum case also satisfied. And the time derivative of the right-hand side wave function is also like here. Then actually two of them, consist of the commutator, the quantum Liouvillean. Then the problem is the time derivative of the influence function. So it's an exponential function and the time integral. So time derivative, you get rid of the one integral, and this part is in front of the influence function. So time derivative of this one consists of these three terms. So I just rewrite. And the first two terms are Liouvillean. And the second term is from the influence function. And the conventional theory, like a Markovian master equation or the non-Markovian master equation or something, make some approximation for this one. And like a second order perturbation theory or Markovian approximation theory or something. But here I don't employ any approximation. I just replace this one like here. So this one is actually defined at T. So I can move in front of the reduced density matrix. So this part I just define rho one. So rho one. And so then in the operator form, so first one is a commutator like here. Then second one is like here. So this is operator form. Then so actually, the rho contains all order cis-bus interaction. Then rho one, I'm sorry, rho one, phi rho one is the same order as the original one, but because I define the rho one without phi, so actually first order rho one is the original. So this is the first order. So anyway, this is the operator form. And this equation is useless if we cannot evaluate rho one. Then in order to evaluate rho one, what I did was I considered the time derivative of the rho one. So this is a definition of the rho one. And the time derivative of this blue dashed line is like here. Because we have an exponential function here, so we have like this additional terms. Then the time derivative of this part, because the time integral is gone, so theta is here, like here. Then again, we have a time derivative of the inference function. Then we have a even more complicated terms than original. Then my strategy is whenever I encounter the complex terms, I just replace like here. So this is a definition. Then so this is a rho one, is the first order original one. Then phi rho one is the same order. As I said, because phi rho 2 is actually second order rho one than the original. Then this is the operator form. Then rho one is here. Then theta rho and rho 2 and here. Then if I define the rho n like here, so actually this terms is rho 0. So you see, so rho 1 is rho 0, rho 2. So in order to evaluate rho 2, I just repeat the same things. Then in this way, I got the hierarchical equation motion. So this is a rho 1 and rho 2, and this is the definition of these terms. Then we go to like here. So this is like a prototype of the pattern we now call hierarchical equation motion. So actually I derived this equation, when I was a PhD student, doctor course. And this is the generalization of the quantum master equation. So I named the doctor equation. And however, the Kubo did not like this name. So therefore, this name, I could not name this one. Then, so later, it's called like a hierarchical equation motion. I still regret, I should insist to call the doctor equation. But anyway, so this hierarchical equation motion, so continue to the infinity. So in some way, we have to truncate. Then what I found was for large n, so n gamma, so we have a simple relationship between the lower hierarchy and hierarchy, deeper hierarchy. Then we can truncate. So we named the terminator. That was about time for the terminator. Then, so this is what's called a hierarchical equation. And as I show you, so I did not make any perturbative approximation. And this is a non-Markovian equation because it's noise correlation E2 minus gamma. And so the reason I could have this hierarchy is the following. By the way, so this has a fluctuation dissipation, so we have a thermal equilibrium states. So the reason we had a hierarchy is the following. So as I said, rho 0 contains all of the system of interaction. Then phi rho 1 is the same order, but then rho 1 is actually the first order rho 1 is the original. Then phi rho 2, rho n, go like here. So actually, conventional perturbative expansion, like the lower first order contain only the second order system bus interaction. But then zero also doesn't contain anything. But this approach, rho zero is exact, contain all order of the system bus interaction. Then rho and rho two, it's opposite way. The number of the system bus interaction is actually decreasing, like here. So it's the opposite from the conventional perturbative approach. And I could have a hierarchy because, E minus gamma 2 like this one. So all of these diagrams have the same relaxation time scale like here. And for large n, actually it is replaced by delta function. That's why I could truncate. And this time constant is actually, it's appearing here, like here. So that's why I have a simple relationships. And so here I introduce like the energy eigenstates, but there is also the coordinate space like here. And coordinate space, we can do also same things. And I'm a bit exceeding the time. I think I had the lost time. And so anyway, so for this Hamiltonian, so in the coordinate space, we introduce what's called the Wigner distribution function. And the detail is not necessary, but the point is that we have a generalization of the what's called the quantum Fokker-Planck or Kramers equation. So now we have a hierarchy of this equation. And so the hierarchy, so this is the phase space P and Q, and this D, dP, and this theta is connecting to different order the hierarchy. And if you are familiar with the Kramers equation, this part is called the Ornstein-Uhlenbeck operator. This Ornstein-Uhlenbeck operator is like divided by 2, it's connecting here. And this is a quantum equation, so we have a quantum Liouvillean, but we have a classical limit. So classical limit of this equation is a generalization of the Kramers equation in the non-Markovian noise. And actually, for some limit, this hierarchy reduced to the here. So if the gamma is very large, we may set n is very small. So if I set n to 0, actually I obtain this one. This is called Caldera-Leggett Fokker-Planck and quantum Fokker-Planck. But this limit, so if gamma is very large, we have to have this condition to have to drop the low temperature correction term. So then if gamma is large, the beta have to be very, very small. That means that this can be applied only for high temperature. So this equation is not useful to study the quantum dynamics. Then for h equal to 0, so we have a Kramers equation like here. Yeah, then I just demonstrated like a high temperature case. But low temperature case, we have these terms. And we can include these terms like separating right here, and the high frequency term is like a delta function. So this is the original hierarchy. But now we introduce more hierarchical members like here. Then we have a hierarchical equation motion. Then so this is the what called hierarchical equation motion now. And here it's much more complicated, but anyway, it works. And so the truncation scheme is also a bit different. So I named it like a Terminator 2. However, my former student Akihito Ishizaki didn't answer to me when I suggested. By the way, so I wrote a perspective article for this hierarchical equation motion about 2 years ago. And surprisingly, this is a top 1% of the academic field of the chemistry. And actually, I spend probably only 10 万円 to write this one. You see how cheap the theory is, So you need only electricity or something. And this 10 万円, I bought a small notebook computer. Anyway, so I now talk about yeah, stop again. Why sometimes stop? Oh, yeah. So there are a variety of applications, but I now talk about quantum thermodynamics. But by the way, I almost forget to tell, using the hierarchical equation motion, I also studied chirality. So like a 2D terahertz magnetic resonance spectroscopy. So now, there is an ultra fast measurement for NMR. So what experimentalists does is they use a terahertz pulse. Terahertz pulse was used to be used for the optical spectroscopy. Like terahertz is like about the vibrational motion for molecule in intermolecular mode, like here. But experimentalists are using the magnetic element of this pulse. So they excite this system magnetically. Then while we calculated using a system bus model, so we computed the 2D spectrum, then we show that the direction of the chiral can be distinguished by using this kind of the measurement. That's what we did. But then now I'm talking about quantum thermodynamics. So introduction. So the quantum mechanics and thermodynamics. And the quantum mechanics like a first principle dynamics theory. Thermodynamics is a phenomenological theory. And the quantum mechanics like a microscopic expectation values are observed. Then the kinetics is important. But thermodynamics, macroscopic variable, the intensive and extensive variables. And also equilibrium states are quasi-equilibrium states. That's a target of thermodynamics. Then, interestingly, quantum mechanics favored by the ordinary scientist. Thermodynamics favored by otaku, in Japanese, in English, geeky scientists. That's why I discovered. So what I call the 熱力学 otaku, they favor it. Then quantum thermodynamics is conducted by ordinary and otaku scientists, both ends. However, it's like in Japanese, 木に竹を継ぐ, so the bamboo and tree are stick like together, like here. It's very strange. Then I saw several strange statements, like a beating kernel efficiency with doing something. Can the second law of the thermodynamics be broken or something? I was very skeptical about this one. So then I thought this could be happen because of the improper treatment of the system bus model. No, like a Lindeblatt is probably no proper approach to study this one. And also improper definition of the thermodynamic quantity. So, if you want to study using quantum mechanics, you have to define the thermodynamics quantity. But this definition is not so clear. So then to clarify this, things, so we decided to do the numerical simulation using hierarchical equation motion, numerically rigorous approach. Then, fortunately, I have a series of the otaku students, and they love to do it, They, if I stop, they keep doing it. Then, so this is proper handling of the system bus model. So, as I say, fluctuation and dissipation we have to think about. And this is thermal equilibrium states, and like here. So, point is that if you work on the thermodynamic system, like the heat engine or something, you have to have a adiabatic process. Adiabatic process, you cut the system bus interaction like here. So then, we have to cut like here. But many, if you start from this factorized initial condition, this effect cannot be included. And as I said, the energy for this one and for this one, oh, I'm sorry, this one and this one is different. So, energy does not conserve, so for this heat engine. Then here, so another thing, what we found another interesting fact is that this open quantum dynamics theory is described by this Hamiltonian. So this is like an isolated system, like a microcanonical statics. This is microcanonical statics follows. However, time irreversible because we consider the infinite number of the heat burst degree of the freedom. Then so the trick is if we make the J of omega to continuous function, as I say, heat capacity is infinite. So therefore, we can study the time irreversible dynamics, also the heat things. Then we discovered, very interesting fact. So this is Mr. Sakamoto. We at the mountain, here mountain, then we saw the sign for Sakamoto. So this is Sakamoto. So anyway, we are calculating the non-equilibrium work. There are two definitions, but we are calculating this definition. Then my student Sakamoto discovered if make the driving force slower and slower, then actually this work agree with the free energy like here. And this free energy is calculated from another approach, like what called the imaginary hierarchical equation motion, but here. So we are wondering why it agree with. Then realize this one. It's called Kelvin-Planck statement. When you learn the thermodynamics, probably you saw this equation. I also saw this equation, but I never pay attention. And some textbooks, put this equation, but they don't explain. So under what condition equality is established? Then we found, for quasi-statics case, this equality agrees, like here. Then if this one is, if we have this identity, then actually we can evaluate the free energy from this dynamical simulation. So we can directly evaluate the free energy from kinetic theory. And this is much, much simpler than the what's called the Jasinski formula, like here. So we define the thermodynamic variable using these free energies. Then, so now we are studying like a Carnot cycle, but then, so we have to have an adiabatic process. So adiabatic process, so we put the adiabatic work, then cut the system bus interaction. Then what we did was that we introduced the time-dependent system bus coupling, A of T, and like here. And we call it the adiabatic transition field. And it looks very simple to introduce, but there is a difficulty to compute because, this A of T, manipulate not just a system variable, also heat burst degree of freedom. So actually, this external field actually, also makes some work for the heat burst. So it's very unusual for the thermodynamics, but the quantum thermodynamics, everything has to be defined by the Hamiltonian. So we believe this should be like this one. Then, so I call it the adiabatic force, but maybe it's better to call it angel force because it's A or something. Then the hierarchical equation motion approach actually can handle this part as well. So can treat the burst part of the energy. So this is a hierarchical equation motion with the adiabatic field. So just replace the time-dependent system bus coupling like here. But point is, so the work now it consists of the two parts. So work is actually derivative of the Hamiltonian, and HA is time dependent, HI is time dependent, but HB is time independent. Actually, so we have to compute these two terms. And HA here, the HB here, the HB system bus interaction, we have the burst coordinate. So to calculate the expectation value, we have a burst coordinate here. Then this part is gone. But however, what we found was hierarchical equation motion. This part is the first member of the hierarchical member. So using that one, we can also evaluate this one. So we can evaluate the total work. Then we can evaluate the free energy for the total system. Then, so that in the quasi-statics case is like here. And the heat burst part is gone. So the free energy is actually equivalent to here. Then once we have a free energy, then temperature derivative of the free energy is entropy, what we call Boltzmann entropy. And internal energy, also the magnetization is external field magnetization, and strain, what we call strain, is also state variable, derivative of the A, like here. So this actually, the Boltzmann entropy is different from what's called the von Neumann entropy. Because the von Neumann entropy, it's isolated system. So you cannot include this kind of the interaction. So we believe this is right, the entropy. And most importantly, these are the extensive thermodynamic variable. Quasi-static, they are the extensive thermodynamic variable. And many quantum dynamics theory or quantum thermodynamics theory, they don't have an extensive variable. But the thermodynamics, you need an intensive and extensive variable. So this is, it's a very natural way. And then actually, this is probably we should call demo because otherwise I enter right here. And then after we obtain this one, then we may have like a PV diagram kind. So for Carnot cycle, I believe that we need to have this kind. Otherwise, it does not look like a Carnot cycle. So this is a P and V, but this case is the external field and magnetization. The other is this angel force and Damon force like here. So we can draw this one. Then, so under this definition, actually, we have this diagram. This is very, you are familiar with, if you are familiar with the thermodynamics, there are four energy like here. So it's called thermodynamics potentials, like a Helmholtz gives the internal like here. Then it goes through relates through the Legendre transformation. Then the change of the internal energy, we can also calculate for the hierarchical equation motion here. Then big problem is the change of the internal energy, the heat burst part. And as I said, the heat burst has an infinite degree of the freedom. So the internal energy is infinite. So, we cannot calculate this. However, we realize actually what we need is not the heat burst energy, but the change of the heat burst energy. That is actually heat. So we can compute the heat to the heat burst from the change of the heat burst energy. And the change of the heat burst energy is actually like this form. It's like this form. So HB and H total commutator is actually like this form. And again, we can compute this one from the hierarchical equation motion. So we can also compute the change of the heat burst energy. So everything we need to, what we need is can be computed from hierarchical equation motion approach. And this is like a relationship between the work and something. Then together with these, we have the first law of the thermodynamics and the second law of the thermodynamics like here. And also we can define the total entropy production here. So it's consistent with the thermodynamics theory. Then we now compute a Carnot cycle and like this one. And I think I'm running out of time. So anyway, so Carnot cycle, it's like a 4-step, the low temperature bus, high temperature bus, and 2 adiabatic process, and the PV like TS diagram here. This case, so the high temperature case, but we have to, this is the first step. Then second step, we are removing the heat burst. So this process, Carnot, it's just assumption. This process, our case is dynamical process, and this should be also quasi-static. So actually, we have some extra step for this one. So our Carnot cycle first, I'm sorry. First step, then second step, the adiabatic process. Then isentropic space actually is we have a isolated space, so we have to change the energy by external force like this way. When I think I could say so. Anyway, it's 8 steps. Then this is the result. So the we change the system bus interaction, weak system bus intermediate, strong system bus interaction case. So it's like a regular Carnot limit. But we have the adiabatic force. But interestingly, the work done for the adiabatic force for high temperature and low temperature are canceled each other for the weak system bus interaction case. So this is like a classical case, regular case. But intermediate strong cases, they are not canceled. So there are some work for the system bus interaction. And the strong case like here. Then so this is the most important case. So we also computed the Carnot efficiency. So it's efficiency as a function of the cycle. So for first cycle to slow cycle. So this is a slow cycle and a fast cycle. For fast cycle, the weak, strong, intermediate interaction, the value is different. But once the cycle getting slower and slower, all of them approaches to the converges to the Carnot limit. Carnot's statement, the efficiency of the heat engine does not depend on the system. So this case, actually this does not depend on the system bus coupling. So it's consistent with the Carnot, theorem. So Carnot is actually right, even in the quantum case. And this is we plot it as a function of the system bus coupling. And the intermediate states, there's always the most efficient place. But anyway, if the cycle is very slow, everything is the same. And now we are extending this thermodynamics to the non-equilibrium processes. So because our theory is a kinetic theory. And we seem to find the way to extend the thermodynamics to non-equilibrium place. It's like a time derivative form, and it's related through the time-dependent Legendre transformation. And this might be the generalization of the thermodynamics in the non-equilibrium regime. So this is now what we are going on. And the conclusion, actually the system bus model, like a microcanonical system, and and irreversible dynamics. It's a very interesting character. And so the key of our theory is this quasi-static free energy. So we evaluate free energy using a non-equilibrium work. And hierarchical equation motion approach is very important because we can treat both isothermal and adiabatic processes like here. And so to do this kind of simulation, you have to use a hierarchical equation motion approach. And so the extension to the non-equilibrium case is now ongoing. And so this is the end of my talk. So there are a lot of collaborators. Thank you very much for the attention.